Absolutely.
Perfect. So I take it everybody else is as well. Welcome to Bay Vision Virtual Meetup. Very happy to have everybody here. We do these meetups about once every other month. Today we have a very special guest speaker, Professor Daniel Rueckert, who will talk about AI and the future of radiology. Before we get started, just a few words about us. So we are RSIP Vision. We're an AI company, and we develop computer vision and visual intelligence solutions for medtech. What do we mean by this? What is visual intelligence for medtech? So today we typically talk about three different areas, three different fields. The first one is surgical planning and in general elevating imaging. For example, constructing 3D models from standard 2D X-rays, using MRI scans to provide high resolution models of bones, or surgical planning, for instance, in orthopedics, detecting landmarks and making measurements to help select surgical implants. This is one aspect of AI in surgical planning, actually not only in the orthopedic field, but in many other verticals. The second aspect is the intraoperative aspect. This can be about surgical navigation. It can be about measurements, automating measurements in a surgical scene, estimating depth, and in general providing tools for orientation during the procedure itself. And then the third aspect here of AI for medical imaging and of the type of solutions that we're very active and working on here at RSIP Vision is analytics. So once we have all of this data, both from the pre-op side and from the intra-op side, and sometimes even from the post-op side, this can all be leveraged to provide insights, to use that data, to make it more accessible to every physician. This is what we're doing here at RSIP Vision. We aim to provide differentiating technologies to global medtech industry leaders, and we have solutions that are integrated in medical devices and have been used in thousands of clinical procedures. We are running this webinar and a bunch of other fora. We have a computer vision news publication to be connected as we can to the wider community, both to the medical community and to the academic community, which is doing so much amazing research and work in AI for radiology and for medical imaging in general. With that, I'll introduce our speaker, Professor Daniel Rueckert, leading AI researcher in medical image processing. Daniel is a professor of visual information processing at Imperial College London, and also a professor for AI in medicine and healthcare at Technical University of Munich. He founded the Biomedical Image Analysis Group, consisting of 4 academics, 15 postdocs, and 20 PhD students, has made more than 500 journal and conference articles, graduated over 50 and mentored over 50 PhD students, and is also the co-founder of Ixico, an Imperial College spin-out company, which is advancing Alzheimer's disease imaging biomarkers. So it's cool to see, Daniel, that you have also this entrepreneurial streak as well. Very much looking forward to your talk. The audience will be able to write in questions, which I'll pass over to the speaker towards the end of the talk. Take it away. I'll make you the presenter, and let's get started. Here we go.
Thank you very much, Moshe. Thanks very much. So I just have to figure out how do I, yeah, okay, I will, hopefully you can see my screen now.
Looking good. Yeah, we see the window.
Okay, so should be now in full screen mode. So yeah, thanks very much for the invitation. I'm very happy to be here tonight, or wherever you are. At least here in Munich, it's already in the evening, and I would like to give you a brief glimpse into what I think might happen in the future of radiology and how AI is probably going to shape that. And I'm going to start off with some newspaper headlines, which I think many of you will have seen, or you will have seen similar ones, which promise a revolution of medicine through AI and machine learning in particular. And it's very interesting to see that a lot of these headlines look like computers or robots will replace, for example, medical doctors. But I will try to convince you that that might not necessarily be the case, because there's also a lot of hype in this field. So I'll start off with one quote, which I think, again, some of you might have seen before. Jeff Hinton, Turing Award winner and one of sort of the founding fathers of modern deep learning, said a couple of years ago, actually 5 years ago, we should stop training radiologists now. And I think if you now look at this 5 years later, we have a huge shortage of radiologists, and we still need a lot of them. In contrast to that, a radiologist, I think, made a very accurate statement about the future. Curtis Langlot said to the question, will AI replace radiology? I say the answer is no, but radiologists who do AI will replace radiologists who don't. And I think that's the key message, perhaps also from this talk, that AI will change how radiology is practiced, but it will not make radiologists obsolete. Now, I'm going to focus very much on radiology as a field, because if you look out into what is commercially available, for example, you see that a lot of the FDA-approved medical devices and algorithms based on AI focus on radiology. So this is really perhaps the field where the transformation through AI has happened very early, and also there's a lot of potential for AI to transform that field. I wanted to just highlight what the opportunities for AI in radiology are, and I will start with what I would call perhaps the top of this value pyramid, where you probably add most value to at least the patient, is by, of course, improving the diagnosis of diseases and, for example, improving screening and monitoring of diseases. So clearly, that is perhaps most valuable from a patient's point of view, and that requires us to have computer-aided decision support systems. That's also quite hard to do in practice, but there are some other tasks which are perhaps easier for AI. And I'm going to list here two. One is, for example, extraction of imaging biomarkers, quantification of measurements from images, or segmenting images or semantically interpreting images. These are tasks which I think we can do already very well with AI, and they're probably slightly less valuable from a direct patient point of view, but they're very valuable from the clinical workflow point of view. The other 2 points which I also wanted to highlight, and I will start off actually with giving you some examples of this, how we can use AI for improving image quality, or acquiring better images or images in a quicker way. And so what I want to do in the next 20 minutes or so is give you an overview of these different aspects in this pyramid and how AI can help. And I'm going to start with the bottom of the pyramid. I'm going to start with how we can acquire images better and faster with AI. And for that, I'm going to give you a quick example of what I want to do. And I will need to explain you a bit about how medical images are acquired, because that's different to computer vision. Typically, images such as MRI images are acquired in a measurement domain. In MRI, that's called the K-space domain, and that is simply the Fourier transform version of the image. So what we do is we sample this K-space, all the frequencies. After we have done the sampling, we can reconstruct our image using a Fourier transform. Now, it turns out that this sampling of K-space has to happen sequentially, and this makes MRI a very slow imaging modality. Now, what can we do in order to acquire the images faster? Well, one way of acquiring the images faster is by not acquiring all measurements in the K-space domain, so not acquiring all frequencies. What you see here at the bottom is I've only acquired 25% of the frequencies, which means I can acquire the image 4 times faster. But if you look at the reconstructed image, you also see that the image quality is poorer, because I violated Nyquist's sampling theorem, and I don't have acquired all the information I should have acquired. So the question is now, can we use a learning algorithm, for example, based on deep learning, to reconstruct a high quality image from this image which is corrupted by artifacts? And I just wanted to highlight that we can do this both either in the k-space domain by trying to estimate the missing lines of k-space, or we can do it in the image domain by trying to remove the aliasing artifacts which you see in these images. So turns out that one can do this quite nicely. One can use a neural network, and I'm just going to show you this here in a schematic to do this. And we can take a low quality image and convert it into a high quality image using this idea. However, it also turns out that we have to be careful how we do this. We have to exploit our knowledge about the image acquisition process in order to do this. So the algorithm I'm going to show you here is an algorithm which we have developed in our group a couple of years ago, and it's based on two different parts of a neural network. In the first part, we are performing in the image domain a denoising or de-aliasing using a block of convolutional layers. And once we have done that, we have an estimate of this image after de-aliasing, but we also would like to make sure that this image is consistent with the measurements we have made. So we add another layer, which are these green blocks here, and that layer transforms our image into k-space and compares our k-space lines in our reconstructed image with the real k-space lines which we have acquired, and tries to make those consistent. And then we keep on repeating this process, interleaving between performing operations in the image domain and performing these data consistency operations in the k-space domain. Now, here I'm going to show you an example how this looks like in a result. So on the left-hand side, you see an undersampled acquisition. You can see it's very poor quality. In the middle, you see the deep learning-based reconstruction, and on the right-hand side, you see a fully sampled image. And you can probably see from this that we can basically reconstruct an image with the same fidelity as the ground truth, but 6 times faster. And this is something which has significant impact because we can now reduce the scan times quite considerably for the patients in the scanner. Now, I also want to show you another application, and now sort of perhaps going one step higher in the pipeline, where we do some semantic interpretation of what images, of what we have actually acquired, for example, in terms of imaging. One application which we work a lot with is trying to help radiologists perform fetal screening during pregnancy, and ensuring that problems during pregnancy are spotted early on. And a key element in this is trying to recognize anatomical features in ultrasound images as these ultrasound images are acquired in real time. And so what we have actually developed is a neural network architecture which takes a video stream of ultrasound and automatically detects whether these ultrasound images are the required views which need to be reported on by sonographers, and then automatically captures these views and performs measurements in these views. Now, this is in principle a relatively easy computer vision task because you can almost use this type of VGG type network or ResNet to do this, and this actually works really well in practice. Hopefully you can see this video here, which shows on the right hand side an ultrasound examination performed in a live scenario, and on the left hand side you can see that we're automatically populating views which have to be acquired by detecting anatomy in these ultrasound images, and then automatically performing these measurements as well. So this can all happen in real time, and this is one of the nice things about using neural networks or convolutional neural networks, that we can do this very, very quickly. One of the things which we have also then sort of looked at is whether we can automatically detect not only which part of the anatomy is in the image, but also where it is in the image, and even do perform localization. And this is something for which we have adopted the use of attention mechanisms or attention models. This is something where we effectively add attention gates to our neural network, and then we can localize very accurately in these ultrasound images, for example, which regions in the image contribute to this being labeled, for example, a 4-chamber view of the heart or a left ventricular outflow tract view of the heart. And if you look at these localization maps, you can see that they are actually very, very detailed and very accurate in terms of localization. And it's quite interesting to see that this works so well, because these models are only trained with image level tags. So we never train these neural networks with any localized information of where organs or part of the anatomy is in the image, and still we can learn this very, very accurately. You can use a very similar idea to also, for example, identify in 3D ultrasound images standard view planes. Here we have coupled this model, which you saw on the previous slide, with some ideas from reinforcement learning, where we now have a agent traversing the ultrasound volume, trying to find an ultrasound view plane which looks like the prescribed view plane, and then automatically performs measurements in this view plane. And this is quite useful, because it saves the radiologist quite a lot of time having to visually inspect an entire 3D volume and scroll through that volume. We can effectively automate that process for them. Now, I think I don't need to explain this audience that we can also do image segmentation with this convolutional neural network architectures. I'm sure you're all very familiar with this. We can organize, we can very accurately localize organs, the anatomy in 3D scans, even if the scans are quite large. For example, here, whole body scans, which are required, but also we can not only segment images, static images, but of course also dynamic information. For example, here, cine MRI, where we can track the heart, and this is important because we want to not only describe the structure of the heart, but also the function of the heart. Now, if you look at the function of the heart, then an important aspect of the function of the heart is emotion. So we have also thought about how can we jointly, for example, track motion in a cine sequence, as well as perform segmentation of that cine sequence. And for this, we use quite now, I think, quite state-of-the-art methods from deep learning for motion tracking, which have been published, for example, approaches such as voxel morph, some of you might be familiar with. And we have then added additional information about what type of object we're tracking, because we know when we track the heart in a sequence of MRI images, that the behavior of the heart has to correspond or has to obey certain biomechanical laws. So one of the things we've been doing is, for example, we have used regularization terms from which are biomechanically inspired, for example, volume preservation, to regularize cardiac motion tracking. And we do this by training a a variational autoencoder, which learns how to regularize motion so it's biomechanically plausible. And then we use this autoencoder to constrain our motion tracking in the heart. So with all of this, you might say, well, actually, you can almost now measure everything. For example, about the human body, for example, in the heart, we can measure the size of the heart, the motion of the heart, the function of the heart. Can we deduce new biological or medical knowledge using this information? And I want to very briefly show you some work which we have been doing using a very large data set from UK Biobank, which is imaging over 100,000 subjects with whole body imaging, with brain imaging, but also with cardiovascular imaging. But more importantly, they also acquire information about lifestyle, genetics, and for example, diseases. And if we now have that, we can put all of this together, we can analyze all these images and look for associations with genetics or disease. And I perhaps just show you this picture because I think this shows quite nicely what we can do with this. We can, for example, identify which parameters of the heart correlate or are associated with, for example, diet, with lifestyle, with physical measures of physical activity, with cognition, but also with medical diseases. And this plot here, which is called the Manhattan plot, shows the strength of these associations or correlations, and also the statistical significance of these correlations. And this is something which you can then use to generate new biological insights. Here's also something which we've contributed to, published in Nature a year ago, where we, for example, used this very large data set and fully automatic analysis to try to identify genetic variants which cause different patterns of this trabeculation in the heart, which are these small branches here in the myocardial muscle. So the final application which I want to show you is that we can, of course, also go to the highest level in the pyramid and sort of do decision support for clinicians, for example, in terms of predicting whether patients have good or poor outcome with a certain disease. I've shown you that we can segment the heart, for example, and segment that not only in one time frame, but also in multiple time frames. And when we use these multiple time frames, when we track the motion, you can display the motion in some form like these spaghettis coming out here out of the right ventricle of the heart. Now, if you combine all that information, for example, in a sort of task-specific autoencoder, we can encode structure and function of the heart using an encoder and decoder, and learn a latent space representation, which is predictive of, for example, outcome for the patient. For example, in this particular case, survival. So here we try to optimize two different loss functions. One is that we would like to reconstruct the data as accurately as possible, but also that we would like to be able to predict outcome or survival of patients. And this is something which you see here. We can do much better with this machine learning model than compared to conventional models. So with that, I just want to very briefly, if I have 3 or 4 more minutes, to also highlight some of the challenges which we're facing and we're currently doing research on. One is obviously that in order to get your algorithms to be used in clinical practice, we need to be able to make them work very robustly and also perhaps verify that they work correctly. For those of you working in computer vision, for example, on autonomous driving, you will be very familiar how difficult it is to formally verify a neural network. So this is something which is really hard, but is absolutely critical we do when we want to take things into the clinic. A second point is that I think we also need to work more on identifying biases in our data and making our models generalize better. So if I use this type of population for training my machine learning algorithm, and then I apply it in the clinic in such a more representative population, then of course we can't be surprised if these models don't work particularly well, if they are heavily biased towards a very small unrepresentative group of the population. And this is especially important in healthcare, where we know that diseases affect certain parts of the population much more than they affect other parts of the population. And the final point is, of course, also machine learning works best if we have large amounts of data. Getting that data is often challenging from a logistical point of view, from a technical point of view, but also from a governance and privacy point of view. And I just wanted to highlight this overview paper here from some of my colleagues, where they show quite nicely that in order to do this, we need to really think about how we not only protect the data which we use for our machine learning models, which you see here at the bottom, but also how we can protect perhaps the algorithms and models against theft, against adversarial manipulation, and so on. And I just want to show you one particular example of where we have sort of shown that this makes really a big difference. In this study, which was published last year in Nature Machine Intelligence, we showed that if we do federated learning, we can, of course, circumvent some of these governance challenges, but federated learning on its own is not sufficient to ensure, for example, privacy. And this is shown on the picture here on the right, where I'm showing in the left column some of the original training data, which was used to train a model. In the middle column, you see some of the images which were reconstructed doing a gradient-based attack on a neural network model. And you can see that you can reconstruct images reasonably well. And if you add additional security mechanisms, such as differential privacy, on the right-hand side, you see that you can no longer really reverse engineer trained models. And this is something which I think is quite important. So with that, I just wanted to finish off by giving you a 1-minute view of what I think might happen in the future. In traditional medical imaging, you have probably seen now this pipeline from acquiring data, reconstructing data, analyzing the data, and then finally interpreting the data. But if we really take a technical point of view, these processes are all entirely serial with no interaction between them. And that's perhaps not ideal. It'd be much better if we use our AI-based approaches to couple acquisition, reconstruction, analysis, and interpretation much more closely together. And I hope that if we do this in the right way, we can optimize perhaps even in an end-to-end fashion each of these steps with respect to the clinical endpoint, because that's what we really care about. And that leads me to perhaps almost the last slide before the acknowledgements, that if we really take this to an extreme, why don't we think about trying to directly go from the acquired signals to the diagnosis, because everything in between is just an intermediate step, which is important because we want to look at the data, for example, from a visual point of view. But actually, the information which is in the reconstructed images is of course also in the quiet signals. So perhaps the question we should really ask ourselves is, do we need images at all? Or could we just perhaps use a very large neural network and reconstruct directly the diagnosis from the acquired data? I don't think this will happen tomorrow, and I also fully aware that there are some downsides to doing this, but I just wanted to put it up here to stimulate the discussion. And with that, I would just like to acknowledge all my collaborators, postdocs, PhD students, both in London and here at TU Munich, and also our funders. And I'd be very happy to answer any questions you might have. Thank you very much.
Thank you so much, Daniel, for sharing all this great work. It's great to see not only the image analysis, but also the way you're correlating it with clinical measures. And maybe eventually, as you mentioned in the end, going beyond images, although I guess for that kind of imageless diagnosis, you know, what would it take for us to trust that? What type of explainability are we as a society going to demand before we get to that point? I had one question going back to the beginning of the talk, of the MRI examples about generalization. So for instance, for the compressed sensing, the MRI reconstruction, is that specific to a particular anatomy or view or sequence, or how general do you think that can get? Similarly for the ultrasound view detection, all right, so how many views can we support? Is it robust to classify a particular view against, call it, everything else? I'm thinking like in orthopedic context, right, if you're looking at trauma cases, so for fractures, there's so much variability of fractures, the data set is never going to cover all that possible variability. So just curious to hear your thoughts on that sort of out of domain generalization, etc.
So that's a very good point. And I think the out of domain generalization has different levels of challenges for different applications. Surprisingly, for the MR reconstruction, which you pointed out, it turns out that these reconstruction methods are relatively robust to domain change. For example, we have shown, and not only we, but also other groups have shown, that, for example, I can train a model with MR images of the knee, and I can then reconstruct brain images. It doesn't, I mean, obviously, you get a slightly higher performance if you train with brain images and you reconstruct brain images, but it's surprising that, you know, knees and brains look very different, that you can reconstruct. I think the reason there, for example, is that you're actually really learning the statistics of small patches and the intensity distribution in the small patches. You actually don't really learn anything about, let's say, the large scale content of the image. It's a bit like dictionary learning. I think you're learning the building blocks of an image without learning the image. Now, your second point, when you said, well, but how does this work when you, for example, then do view classification in the ultrasound images, or you do you know, you look at fractures or other things? There, I think you have a much bigger problem. I think there the domain adaptation is harder, and as you say, even a very large data set doesn't probably cover all types of fractures you can possibly think of. There, I think we need to find better ways than just being purely data driven. Perhaps there we also need to, for example, have an explicit model of the anatomy in it, and then sort of adapt that model of the anatomy to the data we measure. In the case of the MR reconstruction, we don't really want to be too biased to what we expect to see in the images, because if there's half the brain missing, then we should see that in the image. But I think at some point we can only deal with its very large generalization problem if we have a better model of what we expect prior to see in this data.
Yeah, as long as we don't try to go back to feature engineering. I noticed one of the other themes that sort of repeated in your talk was the notion of constraints, right? So in the MR reconstruction, it's constrained to have the same you know, case space, the same known lines in K-space, or I think the one in the cardiac anatomy, right? You had constraints on the physical nature of the anatomy. So yeah, it's great to see that we can still take our domain knowledge and our objective understanding of the domain and bake it into the AI, and that we're not just trying to build black boxes and throw computing power at them. So yeah,
I think that's also an example where I think their computer vision and medical imaging is a bit different, because, for example, I've seen some very nice papers which use, for example, adversarial networks very intelligently to help with the reconstruction of images to make them look more realistic. But more realistic looking isn't necessarily what we're after, correct? If it doesn't reflect the patient's anatomy, it doesn't really help us having a very nice clear image.
Yeah, you can't hallucinate an MRI scan. You got to get it right.
Exactly.
Question from the audience about the last slide. Do we need images at all? Wouldn't it make the whole pipeline less explainable? Typical deep models already lack explainability.
I think it's a very good point. I think there also I should point out that in some sense this was meant to be a bit provocative, but I think there is some element to it, because I think I guess what I really want to say is, at the moment we're reconstructing images, and then so we're reconstructing something very high dimensional, because an image is a high dimensional object, and then we're reducing it again by doing analysis and interpretation into typically very small number of measurements to make then a clinical decision. And I guess the point is that this might not be the optimal way of doing this, because a lot of the information in the image is not relevant to what we're clinically interested in. So there must be, or I would postulate that there's a more effective way of going from the raw sensing data to the information we really want. I don't think that we will really skip the imaging completely, but perhaps the imaging is just a side product. It's something which you use to check the validity of the result, but perhaps there's a much better, more efficient way of getting the original or the real signature which you want from the data. So I'm just saying we can also optimize the pipeline just to do extracting of information. We can still reconstruct an image. Nobody is stopping anybody from trying to at the same time take the signal and also reconstructing an image from it.
But yeah, in the end, if we only care about the diagnosis of a particular patient, then yeah, the system should be focused on that sort of in some end-to-end way. I get it. Yeah, we sort of tried to do something, a very simplified version of that when we did the X-ray-based 3D reconstruction. So what we said is, this is a reconstruction problem, but we don't really care about reconstructing the entire CT, and the information in those X-rays is limited. We only care about the bone models. We only care about segmenting the bone. So we're not going to do it in 2 steps. We just did it in 1 step, sort of end-to-end. We took the X-rays and go directly to bone. So sort of making the AI's life easier by only trying to learn what we really need to get out of these images. Let's see, I got 2 or 3 more questions and 2 or 3 more minutes. So I'm going to choose, I think, one of them. Okay, one question about the adversarial attacks you showed at the end. Are adversarial attacks a good surrogate for the expected imaging variability in clinical settings? So you mentioned, right, robustness.
So actually, I mean, I guess what I really wanted to show with the adversarial attacks on these learned models is not so much the robustness, but that you can potentially have a privacy leakage in this. So, for example, if I just very briefly show this one slide, if you really think about this, if you can reconstruct, for example, from a learned model, I don't know whether you can see my cursor. Can you see my cursor?
Yes, I do. Yeah, it's on the second column there.
Yeah, exactly. On that second column, for example, we have been able to reconstruct this image using an adversarial attack from a learned model. And in this image, you, for example, see that this patient had a mastectomy. So you can infer some knowledge about that patient from, even though the reconstruction looks blurry. and this is problematic. So I think I more wanted to really show here with this adversarial attacks that it is potentially possible to reverse engineer some of the training data from a learned machine learning model.
Yeah, that's obviously a concern. Although the very fact that it's possible to take an ML model and reconstruct a particular training example, right? Besides the privacy concern, this is also concerning in a way in itself, because right, one would think that if this model is capable of generalizing the way we want it to be, maybe it should not be possible to resurrect a particular training example, right? Because it means there's still something about this very low dimensional part of the space that's in a way baked into the model, if it's possible to resurrect it.
This is actually a model which was trained for classification, for image classification, not for image reconstruction. So perhaps because it learns something about classification, it has to learn something of the overall image. So it's but you're absolutely right, it's a bit worrying. Mm-hmm. And that also shows that we sometimes don't really understand what these models really have learned.
Mm-hmm. Yeah, but yeah, they seem to be doing very well nevertheless. So yeah, thank you very much again, Daniel, for your time and for sharing your research and just your insights into where this field is going in general. Thanks very much to the audience for joining us today. Please feel free to reach out over LinkedIn or however you like, and see you all again in 2 months. Thank you again.
Thank you very much for the invitation. Nice to
see you.
Bye.
Pleasure. Bye-bye.